what year was the spread the word to end the word movement started by the Special Olympics?
Oh, they're doing the trivia. You can literally just look at them.
Yeah, that's how trivia works.
Go to those. Whatever day it was.
All right, so you can see this now, right? Okay, cool. Alrighty, so here's the deal. Yesterday we proved that perpendicular bisectors are concurrent. I wanted to review that really quickly. So you already have page 12 written down, correct? More or less, or maybe you didn't write anything. And if you didn't write anything, great. I would encourage you not to, but if you want to write it down now because you got it yesterday, go ahead. This is review, right, for page 12?
So don't write it. Who's putting this in?
Okay, there's a thing back there with the things that are due at the end of the week. If you want to ask that. Okay, so at the end of the week, nothing is due right now. So, perpendicular bisectors. Let's make some, right? Just to be clear, I think this really helps some other classes. Again, I apologize for you being guinea pigs, but that's just how it goes, right? It's just the way it is. All right, so we are allowed to assume for any triangle a midpoint, right? All sides have midpoints. Do we agree? Right? Any segment you can think of, no matter how small, is going to have a middle. Do we agree? So we can say, let there be a midpoint. That's always allowed. Are we also always allowed to connect dots? Like draw a line between two dots? Well, of course, right? So I can always create a median. So vertex to midpoint, I can say let there be, right? And have that happen. That's totally valid. Totally cool. I can also say let there be an orthogonal. I can say this. So vertex to 90. That's an orthogonal. I can always do that, right? Now, maybe the triangle's really weird and the height's outside it, but in general, there's going to be some line that goes from here to this side at 90 degrees. Maybe it's a really weird triangle, and I have to extend this line out so I can get to 90, but there's going to be one that exists, right? It's going to be somewhere. So you can say, let there be there, okay? We usually work with acute triangles, though, because it makes the drawing a lot easier, but it'll work the same for obtuse. So we're allowed to say vertex to 90. We're allowed to say vertex to midpoint. We are also allowed, if we want, to take any triangle and say, look, here's a midpoint, right? Let it be the midpoint. And from there, draw a 90-degree line. We can create a perpendicular bisector whenever we want. That's totally fine. So midpoint going up at 90, right? Midpoint to 90. Totally valid too, right? What is not something you can assume is that, look, I want this to be the midpoint, I want this to go up at 90, and I want it to go to the vertex, right? Because there's an example where that's definitely not true, right? So we cannot assume that. This is vertex to midpoint at 90. So as you can see, two of these things, vertex to midpoint, totally rad. Vertex to 90, totally rad. Midpoint to 90, totally rad. Like any combination of the two. All three at once? No, not always true, so we cannot assume that. We have to prove that, right? If that's the case. So when we're starting this, is everybody cool with this? Do we see that idea? Okay. When we're starting this proof for perpendicular bisectors, we can draw perpendicular bisectors and just assume they exist. That's totally valid. What we can't do is say they're perpendicular, they bisect, and they go to this point. We can't do that. So when I say let there be perpendicular bisectors, totally rad, totally fine. Because I can assume that this is the midpoint of this side, right? There's got to be a midpoint somewhere. And I can also assume, where's my ruler? That there should be some line I can draw to make it perpendicular to AB, right? Where is it? I don't know. Probably about like here, right? So I can say, let there be a perpendicular bisector. Totally fine. So I'm going to do that. Let D, let's call it DE. Needs to go off to somewhere, right? Can't assume it goes to C, so I just drew it. Let DE be the perpendicular bisector. That's my symbol for perpendicular bisector. Is everybody cool with that? Right? It bisects, it's perpendicular. Of line ADB. So I've created that. Oops. ADB. That's a D. Cool. So let that happen. I'm going to create one more. Doesn't matter which one I choose. I'm going to create, how about this one? So midpoint-ish, right? Everybody clear that that double mark right there applies between these 2 points? We cool with that? I know it cuts it there. I don't want to draw a big squiggle. Diagram's going to get gross anyway. So I'm going to say this is point F, and I'm going to draw perpendicular to here, right? Yeah. The overlap with people whining about their grades and not paying attention. The Venn diagram is a circle. It's amazing. All right, so FG, unrelated to you, Bailey. All right, FG. Let FG be perpendicular bisector to AFC. Now, do we agree that these lines intersect somewhere? They're going to, somewhere, right? So it's totally valid to say, look, where they intersect, let that be K. So I'm also going to let FKG and DKE exist. That's just a way of saying, look, they intersect at K, right? Because they share a letter K, so that's where they intersect, right? How do you know that D is on line ADB? Because when I write line ADB, it has that letter in it, right? How do I know that K is on both of these? Well, because K is one of the letters. And if that point's on both lines, then it must be a point where they intersect, right? We cool with that so far? Right? I just drew some perpendicular bisectors, and that's how we say it. Let there be perpendicular bisectors here and here, and let them intersect at K. So far, so good? All right. So what I'm going to prove is if I draw this last perpendicular bisector in, that it also must go through K. Right? I can't assume it does, right? We don't know that. We're trying to prove that they're concurrent. 2 of them are going to intersect at some point. The third one, who knows where it goes, right? I'm going to prove it has to go through K. So how do I do that? Well, we learned the other day about perpendicular bisector theorem. Perpendicular bisector theorem says this. It says if you've got a perpendicular bisector, right, then the distance from here to here will be the same as the distance from here to here. In other words, this point is equidistant to these 2 points, right? So if you have the black, you get the blue. That's perpendicular bisector theorem, also known as perpendicular bisector theorem. The converse is the exact opposite. It says if you got this, if you've got a point that's the same distance from 2 other points, right, on a line segment, then that means that you got this. That's the converse, right? Notice the blue and the black just switch spots here. That's all. So this is perpendicular bisector theorem converse. So let me say it again. If we have a perpendicular bisector, there's a point on it that's equidistant from both sides, right? And if I have the converse, what I'm saying is if I have a point that's equidistant, then it must be on the perpendicular bisector of this side. Cool? I know it's a lot of words and words are hard, but do you see the pictures and how that relates? Okay. So let's go back to this guy. Notice perpendicular bisector, yeah? Cool. K is on it. Any point on this thing will be the same distance to A and B, because A and B are the endpoints of this segment, right? So if I put a point here, it would be equidistant to A and equidistant to B. If I put a point right here, it will also be equidistant to A and equidistant to B. So I'm going to write that in. K is the same distance to A, and it's the same distance to B. Isn't that color satisfying? So these are the same by perpendicular bisector theorem, right? If it's on a perpendicular bisector, it's equidistant to the endpoints. So by perpendicular bisector theorem, AK is congruent to BK. Well, if I turn the triangle, and this is bad because the letters are all upside down, isn't K on this perpendicular bisector? Well, then it should be equidistant to C and A, right? So the same distance here will be the same distance here. So I'm going to draw that in. Boop. So not only are AK and BK congruent, but CK is also congruent to them, right? All by perpendicular bisector theorem. Here's where I'm going to use the converse. Remember, the converse says, where's the thing? This is the converse. If they're equidistant, then that point must be on the perpendicular bisector. Turning the triangle. Is K equidistant from these two endpoints? Is K equidistant from B and C? Yeah, we proved that earlier, right? So K must be on BC's perpendicular bisector by the converse, right? So because they're equidistant, if I were to draw the perpendicular bisector, that's like the midpoint, right? Let's call that point J. If I were to draw the perpendicular bisector, K must be on it. And it is. So the perpendicular bisector of BC goes through K. And the perpendicular bisector of AC goes through K. And the perpendicular bisector of AB goes through K. So they're concurrent at K, right? They all go through K. So I'm going to say by perpendicular bisector theorem converse, K is on the perpendicular bisector. I know words are big and hard, right? On this thing of BC. Here's BC. Here's the perpendicular bisector of BC. It has to be on it. Why? Because it's equidistant from B and C. Right. So if K is on BC, and it's on DE, right? And it's on FG, all my perpendicular bisectors have K in it. If they all have K in it, then they must intersect at K, right? They're concurrent. Therefore, the perpendicular bisectors of triangle ABC are concurrent. Did you make it with me through that? We create perpendicular bisectors. They intersect at some point, right? Then we say, because they're equidistant, right? Or because they're on the perpendicular bisector, they're equidistant, right? And if it's equidistant, here and here, then this perpendicular bisector must also go through K. And then we're done. I'll do it one more time. If you want, you can write it down or take a picture right now. Yeah?
Couldn't you usually draw the perpendicular bisector for BC in the beginning?
Because if I drew it, I can't assume that it goes through K. I don't know where it goes through. I know the first two intersect at some point. That's totally valid, right? They're going to intersect at some point. Let's call it K. How do I know this one also goes through K? I don't. So if I drew it, I would either have to draw it through K to make it realistic, or I would have to draw it off of it and then be like, oh, actually, it does go through K, right? Which I thought would be silly to show you guys, right? Could you do that? Sure. So I'm going to do it one more time, okay? One more time. Let me grab another one of these. All right, so let's create some perpendicular bisectors. Let's create AB's perpendicular bisector first. Actually, let's do BC and AC this time. I think it might be easier to see if I draw the last one in here, okay? So I'm going to say, let there be this guy, right? Perpendicular and bisecting. Notice I'm not assuming it goes through A. So let there be that. Let's call it DE. Let DE be the perpendicular bisector of BDC. Cool. Now I'm going to draw this guy's one. So let's call that point E be the midpoint over here. So it's bisecting and then perpendicular line, right? That looks perpendicular. Whoops, we can't call it E. I already called the point E. Let's go FG. So also let FG be the perpendicular bisector of AFC. Cool. Now we agree, they intersect at some point, right? They're going to. They both go through the triangle, so they're going to go and intersect in some point. What should we call that point? T for Taylor. I know some of you are really pissed right now about that choice, but you're just going to have to live with it. So we're going to call that FTG and DTE. Okay? Just showing that those two, FG and DE, they intersect at T. Okay? Cool. Well, isn't T on this perpendicular bisector? Right? So by perpendicular bisector theorem, it should be equidistant to the sides here, right? The perpendicular bisector is coming out of BC, so any point on that bisector is going to be equidistant to C and B, any point on it, including T. So I'm going to draw a line from T to C, and a line from T to B. And we know those distances will be equal by perpendicular bisector theorem. TC congruent to TB. Also, isn't T on this perpendicular bisector? Well, that perpendicular bisector is coming from AC. So any point on here is going to be the same distance to A and C, including T. It's going to be the same distance to C as it is to A. So I'm going to draw that in. If you guys remember, perpendicular bisectors make the circumcenter, and the circumcenter is always equidistant to the vertices because there's a circumcircle that goes around it, right? So I'm just drawing in my radii, essentially. I don't know if that helps or if that's not helpful. So it's also congruent to AT, or TA. Cool. So now's where I use the converse of the perpendicular bisector theorem. Because T is equidistant from A and B, it must be on the perpendicular bisector of AB. Because it's equidistant from these two, it should be on this guy's perpendicular bisector too. So, by the converse of the perpendicular bisector theorem, when I draw in my perpendicular bisector here, it should also go through T, and it do. So T, whoops, is on the perpendicular bisector of which side? Which side's perpendicular bisectors? AGB.
AGB? I mean AJB.
AJB, yep. You can say AJB or just AB, that's fine. You had like a GIF or GIF moment there. It's GIF. We're done. Technically, this is not a hard proof. It's only a couple lines. The beginning's always the same, the middle's always the same, and the end's always the same. You just pick which ones you want to draw in. It is hard if you don't see it, which is 90% of geometry. Which is why I structure my class in a way where I don't want you to have to take notes. I want you to be able to watch the show. If I just slapped this down and was like, here, copy this down, you'd be like, wait, why? But if you watch it in action, it gets better, which is why video is a really useful thing. So if you're struggling with this stuff and you don't see it yet, that's okay. Seeing it is all of the battle. Meaning once you see it, it's like, oh my God, this is easy. But until you see it, it's absolutely impossible. It's like one of those things where you have to like scoot your head in, right? And like when you scoot real close and then pull back, then you can see the hidden image. You guys ever done one of those? Right? Or it's like the question where I have like a bunch of triangles on the board and I ask you, how many triangles are there? And everybody says 3, right? When in reality there's 5. It's not because you don't know what a triangle is. It's not because you don't know how to count to 5. It's because you just don't see it yet. That's 90% of geometry. So if you don't see it yet, you're going to feel hopeless because 90% of the battle you're losing. But as soon as you see it, it's like, oh my God, easy A. I can help you. I can. I've had a bunch of people come in the last 2 weeks and learn the last 2 weeks of material in about 30 minutes. I had one kid come in and learn all of last week's material in 10 minutes because they just watched the whole time and asked questions. And then they're like, oh, that's it? And I'm like, yeah, that's it. A lot of the kids that bomb the quizzes come in, and after they come in and they get help, they go, really, that's it? That's all it was on the quiz? And I go, yeah, it literally was. And then I hand them the quiz and they do really well when they review with me. So here's an idea. review with me before the quiz instead of after. Make your life a lot easier. If you're not feeling like things are going to go well Friday, you should come and see me. I'm going to be here super late again tonight. I was here until 6:30 last night. And I'll do it again Thursday. I will stay as late as need be. I want to make sure you guys get this. If you don't want to stay late, literally when I review with you, I do the same thing I do here. Watch the video. Try that. Can't hurt. Maybe it doesn't work. Then you know it doesn't work. Come and see me. Right? But that's it. Let's move on to another one. The last page in the packet. We're almost done. Now, my page looks a little bit different from yours. I highlighted this triangle so it's easier to see. Before we get to this, I have a little bit of a lemma to remind you of. We've already done this lemma. Okay? A couple weeks ago, we had this proof. We had a triangle, and all the sides were given to us as midpoints. And in that triangle, we connected the midpoints, and that was given to you. And it said, prove something like that this side right here is half of the bottom side, right? Remember that 2-to-1 ratio, right? And we proved it was half and half. In fact, this side will always be half of this side, and this side will always be half of this. Now, does every side always have a midpoint? No matter what line I draw, will it have a midpoint? Of course, right? So every triangle has a hidden triangle inside of it like this. That's going to be half its sides, right? Not only that, we proved that this side will always be parallel to this side. This side will always be parallel to this side. And this side will always be parallel to this side. Always. And we proved that. We're going to assume that to be true. What we call this triangle is a medial triangle because it's made up of the mid-segments of a triangle. Mid-segments are when you connect midpoint to midpoint, okay? You don't really need to know the name, but that's what it is, medial triangle. So there's a medial triangle theorem that says if you have a triangle, you can draw another one inside it, connecting the midpoints, and they'll be half of the opposite sides. And they'll be parallel. So you get all that information for free. Here's what we're going to do today. We're going to have a random triangle. And instead of finding its medial triangle, we're going to do this. We're going to draw a line that's parallel to this side, over here. And we're going to draw a line that's parallel to this side, over here. And we're going to draw a line that's parallel to this side, over here. And it's going to create another triangle, isn't it? And we know that this side is going to be twice as big as that side. And parallel, right? Because we said it was parallel. And we know this side, this one right here, is going to be twice as big as this one. And we know this side is going to be twice as big as this one. Okay? Now, if I called my original triangle ABC, right? My original. Isn't A, B, and C the midpoints of my big triangle? It is, isn't it? So if I were to draw a line like this straight up at 90, what kind of line did I just draw? Perpendicular bisector. And if I were to draw a line, say like this straight up at 90, what line is that? Perpendicular bisector of this side, right? Same thing here. And notice they all intersect at one point. We proved that on the last page, right? Perpendicular bisectors of a triangle are always concurrent. Now, I'm going to do it a couple times. So if you're not getting it right now, hang on. This is the weird part. If these two sides are parallel, I drew a line that goes through them. It's a transversal, isn't it? These two lines are parallel. This right here is 90. Let me highlight that. That angle right there is 90. These two are parallel. This is 90 by alternate interior angles theorem. They're on sorry, not that one, this one. They're both 90, but that's the one I want you to look at, okay? Alternate interior. They're on opposite sides, right? And they're inside the parallels. I can do that for all of them. Now, question. Vertex to 90 in my original triangle. What kind of line is that? Vertex to 90 in my original triangle. Come on, Jerica. You learned it earlier. You mastered them. It's an orthogonal. And if I do the same thing here, that's an orthogonal. And if I do the same thing here, that's an orthogonal. So this perpendicular bisector, a piece of it is the orthogonal of the original triangle. And we know the perpendicular bisectors all intersect here, right? And pieces of the perpendicular bisectors also intersect here. And what are those pieces? Orthogonals. So I just proved the orthogonals are concurrent. Because the perpendicular bisectors of the big triangle are concurrent. So the orthogonals of the small one are. In other words, the circumcenter of the big triangle is the orthocenter of the small one.
That's amazing.
Always. Ready to see it again? The words to write this proof are actually not that hard. It's mostly the seeing it. So I'm going to focus on that today. Okay? If we don't have time to do the words, I'll do that in the review tomorrow, first thing. Okay? So, page 13. To prove the orthogonals of this triangle are concurrent, I'm going to construct a bigger triangle and prove the perpendicular bisectors are concurrent, right? And then I win. So let's do that. I'm going to draw a line that's parallel to CB. So let's get out the ruler. I need more room. All right, so this will be parallel, guaranteed. Super big. Super big. So these two are parallel. Cool with that? Let there be a parallel line. I'll give letters to it later, okay? We can always create a parallel line. I just did, right? How about parallel to this guy? Looks like that. I'm going to slide it over a bit. These guys are now parallel. So far, so good? Next one. What color should I use?
Orange.
Orange? It's Taylor's Day. It's Taylor's Day. Taylor's choice. What an idiot. All right.
They look beautiful. Oh, the green's just gonna grow.
We'll just turn the marker and pretend that didn't happen. So those are parallel. Now that created another triangle, right? Here's point A, point B, and point C. Cool. Now, we know that's the medial triangle of triangle DEF, right? Because it's all parallel. Which means that this side right here is half of this side, right? And it means that this side right here is half of this side. And it means finally that this side right here, 1, 2, 3, is half of this side. Cool? So by definition, aren't C, B, and A the midpoints of DE, midpoint of FE, and midpoint of DF?
Yes.
So those are the midpoints. Let's construct a perpendicular bisector for this guy. A couple of them. Here we go. I'm going to draw them. Perpendicular bisector. It's the song. You have to sing it when you do it. Perpendicular bisector. Woo! Sing it to the tune of Bad Guy. I'm the perpendicular bisector. I might do something like perpendicular. Okay. So this is the right angle. Right? Now, these two are parallel, yeah? You with me? These two are parallel, two blues? The line I made, isn't that a transversal?
Yes.
So by alternate interior angles, this must also be 90.
There's both a lot going on in the second and not a lot.
I know. Watch closely. It's like magic, okay? Yep. So, I'm going to highlight this part of this line, okay? This part right here.
Oh my god,
that's an orthogonal of the original triangle. Cool? We cool with that?
Wait. No, never mind. That was stupid.
There's no stupid question.
That's right.
No, but I know the answer.
Only stupid people. No, just kidding. No, there are none. There are none.
Jericho is so stupid.
No. All right. I'm going to draw the perpendicular bisector over here, right? Ready? Are you ready? All right.
No.
Woo!
Wow.
Okay, shut up, Jerica. I say this with everyone in mind.
I want to be a spinny chick.
I'm the voice of the people. So that's 90. These two are parallel, which means this is a transversal, which means this is 90 by alternate interior angles theorem. Jerica, I swear to God. So I'm going to highlight this portion of it. That's an orthogonal of our original triangle, right? That's the height of the original triangle, right?
It's an orthogonal.
Now, where do they intersect?
The ortho side
The-
through.
Here.
Yeah, what she said.
Coward.
Now, I'm going to prove that the last one has to go through that too. Right? I'm going to draw the last perpendicular bisector.
Oh my gosh, and it's going to be an orthogonal.
These two, right? This is the midpoint. So I draw 90 degrees from here. You do it as best as I can. As best as I can.
Did you say
Oh,
asbestos?
I did.
love asbestos. It's delicious.
My grandpa died of mesothelioma. That's insensitive.
Asbestos is mold. Yeah.
He actually did.
Oh,
Didn't we think
that's
that
how
lemon was poisoned by the mold in our school?
So that's 90 degrees because I made a perpendicular bisector.
I legitimately.
Shut up.
I saw her straight.
Perpendicular bisector.
I love that.
These two are parallel, ladies. I'm serious. Shut up. These two are parallel. That's a transversal. So by alternate interior angles, that must be 90 as well. These two go together, right? So this must be an orthogonal because it's going from the vertex to 90, right? And where do they all intersect? Here.
I feel like
So because our perpendicular bisectors are concurrent, the orthogonals have to be too.
yes.
So how would I write this
The
proof?
orthogonals are always going to be correct.
Okay. How would I write this proof? Here's what I would say. Let me grab another one of these.
I'm literally wheezing. It's okay, Taylor.
Okay. Here's what we're going to do. Let there be some parallel lines. So let's say, let this guy right here, where's my ruler? Let's write it down here. We're going to run out of room. We'll call this DBE. Be parallel to what? What is that line parallel to?
AC.
Good. Okay. Now I'm not going to call it DBE yet. I'm going to put the D and the E in later when they intersect, okay? I'm going to do the same thing for here. Oh, wait. Hold on.
Purple. Make up your mind.
Hannah's not even watching.
What's that? This one? I like purple.
What an absolute scumbag.
I literally love purple. Just kidding. I just pranked you.
That color's really pretty. Maybe I should pick that.
I think purple's my favorite color.
Shut up. No one cares.
The next one would be like pink, like
All right. I use D and E, so I'm going to use F and G next.
like peach.
Oh, God. This is bad. We're going to spell it GAF.
Yeah, like coral. Yeah.
And what is it parallel to?
CB.
CB.
This is the same one as peach. Coral. Coral. No, the peach.
The pig.
No, it's yellow. Disgusting. Are you colorblind?
Yellow is my favorite.
No,
That's literally
it's
orange.
orange. It's
There
that's
you go.
fine. That's alright. I guess.
That's literally
That's
peach.
not what we were going for.
All right. Now I'm going to draw a line that's parallel here.
Coral.
That's approximately
All
parallel.
those colors are not gonna go.
He's
well
doing his
together.
best.
I am doing my best.
Not really.
Oh
though.
gosh,
He's
no,
trying.
no.
Yeah, your
Yeah,
best kind of
kind
sucks.
of cute.
Just kidding.
All right, I already used F and G. Next up is HI, but I don't use I because I is just a sideways H. And depending which way you look at it, it's different, right? So I'm going to use JK.
JK.
And it goes through C.
ABC.
Parallel to what side?
AB.
AB.
JK. Just kidding.
All right. So we know those are parallel. Parallel symbol, parallel symbol. I don't care if you include the parallel symbols, but I'm drawing them just so you don't get confused. Probably.
No, it looks like
I don't know where the pretty purple went. There we went.
it's like it's like
I don't like those
it's like
colors
monogram.
together.
Yeah, it's like
Okay.
a chick who just got a bullet.
So let these be parallel. Now, we know by medial triangle theorem, that's the middle guy, right? So by medial triangle theorem, converse,
I'm not writing this.
Is this in our?
no, you shouldn't. By medial triangle theorem, converse, we get all this stuff, right? Those are congruent. Those are congruent. And these are congruent. Now let's put in our points. I forgot to put in my dots. What do we call these dots? We said DBE, so DBE. Oh, God. Hold on. DBE. Let's change our letters up. Because now this is not GAF, or G. It's going to be FAE.
We're so good.
Yeah, sorry, guys. I tried to big brain this. And this is going to be FCD, right?
Guys, today we have to be nice. Miss Bergman told us that we have to
Cool.
be nice. She kind of scared me.
Shut up.
Very intensely.
Oh, that's not nice.
So,
That's not very nice.
just so we're clear,
That's not inclusive.
You have
Right.
to say it to everyone. It wasn't even-
so what do we write? We write that FC concurrent to FD concurrent to AB. I'm going to only write one of these.
Maybe Taylor's not so bad sometimes.
That's not fair.
And I do that for all of these. So I'd say these are congruent, right? And I'd say these are congruent. Can you write that? Excellent. So I'm not going to waste my time with that, et cetera, et cetera. Okay? Now, let there be perpendicular bisectors. So, let this line exist. Boop. Let's call that, we haven't used what letter yet? We've used F, D, and E. Let's call it G. So let CG be the perpendicular bisector of what? What was CG the perpendicular bisector of?
AB.
Try again.
FD.
FD.
Sorry.
I'm going to do that for all of these. So I'm going to draw this in. I'll call it J. Oh no.
Can I do this one too?
Call it C for chair.
Which we already have a C.
Okay, then call it.
B of what? BJ was the perpendicular bisector of what?
DE.
DE. Nice.
What?
And then one more. I need to draw the perpendicular bisector of the purple side.
FE.
So AK is the perpendicular bisector of FE. Cool. Then we say, since perpendicular bisectors are concurrent, C, let's call that point K. CK,
We already have a K.
no we don't.
Yes, we do.
Oh, we do.
Call it.
L
No.
for
S.
losers.
S.
CL, this line right here.
What about S from? S's look like.
AL,
I feel like Z never gets any attention.
and BL
My favorite letter
are
is
concurrent.
the way you write it in cursive. No, it's because Justice didn't even think about that. So,
And then we got to do alternate interior angles, right?
'cause I like it when I write in cursive. See what it's less.
So I've got those right from this. Now I do alternate interior angles theorem. So this and this will be 90 because they're alternate sides of the line I drew. And this will be 90. And this will be 90. So by alternate interior angles theorem, angle LCD is congruent to angle A. Oh, we got to put a point there. This is fun. Need another letter.
C M for Michaela because she was
AML.
chilling.
Look up to
Camel.
and see if it's. Oh wait, that's
Sort of.
Today.
This angle, what angle's this? LBE.
I'll be okay.
Ladies, zip it. Because you're going to be the same ones crying on Friday.
You're right.
LBE.
Hey, I was laughing. I went to the bathroom to cry.
That's this angle right here. Congruent to L something C. What should we call this point?
P.
N. L and C. Angle this guy right here. LAF. Laugh. Congruent to what angle?
I can't even see.
This one right here.
You have to zoom in. No, there's just so much C.
We're going to call it L something B. What letter?
Q.
Q.
R. S. U.
B.
W.
S.
Y.
Okay, shut up.
A. Shut.
Therefore, orthogonals of triangle ABC
Are concurrent.
are concurrent.
Oh my
Yeah. Aren't all orthogonals always concurrent?
Yep, we just proved it.
Yeah.
So it looks like a lot because I used the bottom of the page instead of the top. 3 parts. Construct your perpendiculars. Use medial theorem. Sorry, 4 parts. Construct your perpendicular bisectors. And then line up your angles using double AIA, right? Alternate interior angles. There it is. Take a picture.
So that is this paper?
I'll zoom in at the bottom so you can get a good picture of this. Because all the top is just parallel lines.
Yeah, your head's in the way.
Yeah,
I'm gonna take a picture of this and no one never even look at it.
I could have wrote that. I'll just screenshot it later on mine.
Oh, now you have a picture. You can
Yeah,
that's on
fancy
corner.
picture.
Can I take a picture of the triangle?
Yep. Once everybody's done with the bottom.
Look at Mr. Matt.
Everyone hurry up.
Here in my picture.
Secretly just is my flash on? That's a little weird. Hold on, let me turn it on.
Yeah, I used to have a meme page, and then whoever was running that totally dropped the ball. I called them out, and they're like, "Oh, don't you worry, we'll have good ones," and then they never did.
Wait, yeah, was it Aiden? I feel like
Not
it was
telling.
Aiden.
Was it Danny?
Not telling.
Bag.
Are we good? Do we have to use the flash?
Wait, what is it for?
Top-notch morons. All right. Are we ready to go? This one. Again, good luck understanding what that is after you're done, but during. Parallel lines, these guys are congruent, and then you've got to draw on your 90s.
Start to see pictures with your flash.
This is definitely the most involved proof. But it's really just the first part of the one we did last time, right? The last page. Plus a little bit more.
Oh wait, I don't think I saved the bottom part. Oh yeah, I did.
We good? All right. I promised I'd show you it one more time. I don't think we're going to have time to do that today. Let's see. 57.
You have 1 minute.
Yep. We'll do this tomorrow, first thing, as part of the review. Okay? And then we'll go back and hit the rest of the packet. My advice to you is if you haven't looked at the beginning of the packet since last week, I would start looking at that again. We'll start at the page 13 review for tomorrow.
57.
This was right before.
So I
really
should
didn't
all
have
have
to
to
have a
put
flash
flash
on.
I have one more thing for you, a little bit of homework. If you want it.
Everyone, guys, when he walks in, just start taking pictures with his flash on.
No, it's so
Everyone,
weird.
here, I want to feel funny. He gets so mad.
He does.
He like tops his head a little.
3 homework problems.
Taylor.
Because you whine so much for it.
Come on, we look so cute.
Whoa, we got one more.
I actually, they're a deep
Do it or don't, I don't care, but
This
it's
is
do
free
it
points,
right.
right?
It's what?
Free points, right?
Not 3 points.
Basically.
You gotta do it.
Well, yeah, if I do it. We do it together. Free points.
Also, there will be problems similar to this on the quiz. It's just applications of what we already
Oh my
know.
God. You don't even live in California.
Trust me, it looks really complex. Once you see it, it won't be. It's some of the easiest stuff we've done. Like all year. Nope, don't go yet.
The quiz. You always say your other.
For number 1,
I know. I don't think
what center must G be for number 1? Ladies in the front, shut up. I'm splitting you up after this week. I can't stand it anymore.
I've been real quiet.
It's not good for your education.
Yeah,
Mm-mm.
you're probably right.
I said I wanted to.
Orthocenter.
That's not a good sign.
It's not.
What kind of center must G be?
If you move me to the back, I won't be able to see anything.
It's the angle bisector one. I need you to be aware of that.
In center.
In center, that's what
as
I
far away from them as possible.
Mr. Mack, if you move me to the back, I
I've
won't be
been
able to
good lately,
see.
and my
You've been great.
He's
No, you have not. You were wrong today.
You're annoying me and everybody else.
Well,
And that's okay.
yeah.
But we're going to change it.